Okay, hello everyone, welcome to our paper club. Today we are going to talk about a flow-based graph generation model, paper from actually 2 years ago from ICLR. Pretty cool paper because they use a lot of different techniques from deep learning. The math isn't too complicated, but because there are so many different areas, hopefully we'll have a discussion about each part. Let's begin. So, my name is Vahan. I'm presenting today for the record. Yeah. Cool. So let's talk about this paper. So the idea here is that we are going to train a model that learns how to generate molecules. So there are two main goals here, right? One is to generate a valid molecule, the molecule that will actually be molecule in real life. The other goal is to make it have desirable properties, because especially in recent years, there have been countless applications for molecule generation. So this paper uses a number of techniques. First, it's autoregressive. We'll talk about the details, what autoregressive means, but basically it generates one node and one edge at a time. But it's also very efficient because they do this affine transform, affine mapping trick borrowed from another paper, which makes the process very efficient. But also, of course, because molecules are graphs, they have to use graph neural networks to learn embeddings for each node, but also for the current graph. Okay, so let's go down into the details. So they also use reinforcement learning to optimize the molecule to have the properties we want it to have. They also have fixed rules, which will make sure that the molecule is valid. So there are a number of tricks thrown into the method to make sure it does what we want it to do. I also looked at the citations, papers that cite this paper, and I haven't found any newer versions of this. Maybe there are, I didn't see any, so that's a good sign, right? It means it's a pretty good state of the art still after 2 years. Cool. So let's start with looking at existing methods. So they have a nice table here where they cover different methods and what they do and then what they don't do. So one well-studied approach is variational autoencoders. So these top two use variational autoencoders to generate graphs. So those are good. The only problem is that they are not efficient at all. There is this Rnn approach, from which they borrow ideas actually. The Rnn approach, which is, I think, the main reference in this paper. They cite this paper, this mRnn paper, quite a lot. I haven't read the other paper, but the difference is that instead of an RNN, they have a graph neural network generating embeddings for the nodes. That's as far as I understand. Mm-hmm. And the flow-based one is this paper. No, flow-based one is this paper, but also there is this graph MVP, which is also flow-based. We'll talk about flows a bit because I found it a bit different from what I expected, but flow is the main idea here also. We'll talk about the math, what flow means. The sampling process, this is all actually very important. So the main drawback of the other flow-based method is that it's one-shot sampling, right? Which makes the quality of the samples not good at all. We'll look at the experimental paper results later, but that's what they also improve here because they do iterative sampling. So they sample better quality nodes. The training process, they claim that this training process here is a lot more efficient than the others because they can train, they do a masking trick, which is quite common these days. They mask a node and then they train those, which means they can train in parallel, which makes training a lot more efficient. Okay. I think that's the summary of the techniques. Any comments here? I don't see anything in the chat, but.
Well, one thing I had that I thought was just like a question is if you look in the introduction in the first paragraph or on the first page, they say that the search space of molecules is 10 to the 33.
Oh yeah.
And I was thinking that I guess that assumes that there's like a maximum molecule size, right? Because if there's no maximum molecule size, the search space is infinite.
Well, maybe they assume. Oh, so maybe in theory there is no maximum size, but maybe there is a maximum largest known molecule. But also in their algorithm, they have a largest limit. There is a limit you set for the molecule size, right?
It's a good question, actually. What do they refer to as the limit? Is it like
some practical number? I'm guessing because even in their paper, in their method, they have two criteria to stop generating nodes. Yeah, nodes, which is either the limit you set in advance or your model says no more nodes.
Or something like valency, which I didn't exactly.
I didn't understand that valency. I think it's a biology term. Chemistry.
Yeah. But also biological, because it harms you. If you have if it reaches a certain level, it becomes like that. Yeah. Biological.
We'll talk about the size actually also in experiments because they experiment on different data sets and they all have heavy molecules, which I think are the large ones, right? This is what heavy means.
Yeah.
Right? Heavy molecules means big ones.
Yeah, heavy in terms of size.
I mean, again, I'm not a biologist or chemist, but I think but they mention heavy molecules in the database, which I guess means molecules, the large. Yeah, I think so. But yeah, that's actually pretty cool that the 10 to the power 33 is really huge.
Yeah.
So obviously we can't brute force this.
Yeah.
Cool. Any other comments? Anything else I missed important?
I don't think so.
No? Cool. So that's about related work. Let's talk about the flow part. What does autoregressive flow mean? So when I read the title first, I thought flow means flow network. So I was expecting to have a directed graph in the molecule, which was a bit weird, but what actually flow means here is that they define a mapping between the base distribution, which will be Gaussian, and the observational space. Okay, so this mapping will first we sample a random variable from a Gaussian, which parameters we have trained before. And then from that sample, we can generate an observational space. So it could be that those are the nodes.
I think you just assume a distribution for the Gaussian. I don't think that you learn it. Maybe you do as part of the training process.
I think you learn the mean and variance, but we'll see.
So can you always just rescale it to one?
Yeah. True. Well, so these the whole idea is that the transformation between the Gaussian distribution and the other distribution is volume preserving. So that whole multiplied by the determinant of that gradient is so that the volume of the space is preserved, or like the.
But it's also the rule, right?
Well, the reason the rule exists is so that if you integrate it over the z space, you would still get probability, like the total probability would equal to 1.
Yeah.
So this is just to preserve the volume of the space.
Yeah. Right. And then since we spoke about this formula, as you see, we have inverses of the mapping, right? So we want to find the mapping or define a mapping that's invertible and cheaply invertible, which is why we talk about affine flow. So affine means linear, really. And we define it right down here. So given an epsilon, it's linear in epsilon. Affine basically means linear, but in higher dimensional space. But the mu and the alpha are mu is the mean of the Gaussian we used, and what's alpha? Alpha is the deviation.
Yeah, I think
Right.
you're right. Actually, you do learn the meaning and variance.
Yeah, I think you learned.
What was actually the again? That was a noise term.
Yeah, it's like a Gaussian. It's a sample from a Gaussian that has a mean of 0 and a
Yeah.
standard deviation of 1.
And so essentially what you're saying is the noise could be directional because alpha E could essentially amplify one direction of noise.
Yeah, and then you can do the inverse of this function, basically given the z, find epsilon, right? Which is that's important. Otherwise, we can't efficiently compute the probability distribution here, density function here.
One thing that I had to think about for a while, which then was was that the dimensionality of z and epsilon have to be the same.
Yes.
Because otherwise you couldn't calculate the determinant, for example. So that's like one element of this that. So for
What
example,
is the dimension of z here?
what is the it's the embedding space for the graphs.
Embedding size. So you define it in advance.
Yeah, it's just that wasn't obvious to me from this until I thought, like when I was looking at the equation. It's like,
Yeah.
It's a bit funny, right? Because this clearly only works if that's a continuous variable and if it has some sort of volume it kind of gets counted.
Then we will make it continuous because it's not necessarily continuous.
Yeah.
Right. We will make it continuous by adding noise.
Yeah. It's just kind of fun, right? But I was thinking, why not map it to quantiles? So then quantiles you can always translate back also to discrete distribution.
We actually do that, eh? We use quantiles.
yeah. One thing that was a detail of how autoregressive flow works was that the two neural networks, G of mu and G of alpha, are unconstrained and positive scalar functions of Z. It says it like right at, you've underlined it in your paper.
Yeah. Which one?
See that on page 3, not the bottom thing you underlined, the thing right above it. It says
This. Yeah.
I was wondering, why does G of mu have to be a positive scalar function? Like, can't it map to a negative mean? Like, why does the mean have to be a positive number?
Yeah.
Just normalize, I guess.
Yeah,
It's not. Yeah.
I don't know.
But you normalize over Z, right? So whether Z is on the negative side of your space, matter.
Yeah.
I didn't think of that. I was thinking more about the space that is Z from. So it's functions of Z. So these are functions of Z generated before that, which is the autoregressive part. Yeah, but I don't know why positive matters.
Because for the variance, it makes sense, but not for the mean.
Well, not really, right? Because you have alpha d squared. So whatever.
Oh yeah, right.
Is,
It could be anything.
but this might be just so you don't map the same 2 points to the same variance. Maybe that causes some sort of solution.
Oh, maybe it's about the inversibility.
Possibly, yeah.
Could be. Right. Okay, so here I wrote down the process briefly. Basically, because the Jacobian here is a triangular, I didn't do the math to see why it's triangular, but I think it makes sense. What we do is
it's because since it's autoregressive, like one variable of Z is only dependent on one variable of
right.
E.
Yeah.
And then so for the second one, it's dependent on 2 and 3 and 4. So you can order the dimensions such that it's triangular.
Also, you switch the rows.
Yeah.
So just enforce the directionality in your page.
Yeah.
But that's important because I was thinking the other way around. I was thinking because the Jacobian is triangular, because of that we can compute the Z's in an autoregressive manner. So first we sample an epsilon, and then from that we get a Z1, and then the Z2, and then so on, to generate the entire Z.
So the epsilon was still a vector here, right? So
Epsilon is a noise vector.
Isn't
and we do know the number of z's we want to predict before.
It's the same.
there's a dimension of each
The dimension
embedding.
is the same of the epsilon and the.
With molecules, we don't necessarily know how many degrees freedom the molecules are.
No, that's not the molecule size. That's the embedding size, I think. The molecule size is how many nodes you add, right?
And I guess
Then you
Z is a graph embedding, right?
no node embedding.
Node embedding or graph embedding? Because then that
Node embedding.
okay, node embedding.
Because then you generate nodes. Oh wait, no.
No, it's a full graph. You
So
generate
does
a Z for each node.
I think you generate Z for each graph, but I'm not sure. Well, I think we'll figure it out as we go through.
I thought you generate Z for each node,
Each node.
and then you end up with a graph.
Yeah, and the graph is the embedding, no?
Yes.
Not sure.
Thanks.
Yes.
The mystery lingers.
Yeah.
But there is a reason we have this discussion, right? So
It
because,
doesn't even take three very long.
yeah, it's like there isn't a lot of math, but they do many different techniques, which makes it interesting and a bit difficult. Okay, let's go to the algorithm, and then we will find out. So next part, the graph representation learning. We have done many papers. There is nothing new here really. So you have a graph, Adjacency matrix, feature matrix. The interesting thing is that adjacency is a tensor, not a matrix, because it's because you have edge types. They allow edge types, and then so that you can have different types of connections between nodes. That's important for the molecule database. I think in experiments you have like two types, but they also have no edge also as a type of an edge. So they model no edge also as a type. Right.
So when you're generating, you have nodes that
No,
are
Yeah.
So it's like a 3D thing, like a cube of adjacency.
Yeah. So which means even if in your specific case you have only one type of edge, you still have to model as a tensor. Right? Cool. So that's the we can actually see here. So this X is the node embedding vector. In dimensions are n. The n is the number of nodes. No, wait.
it's the number of types of n is the number of nodes and d is the number of types of nodes.
Right, number of types of nodes. So here we have d.
Because it's 0, 1, yeah.
So we generate
One hot encodings
K
for types of nodes.
No.
For each.
one node in
As in for each node. So if there was a hydrogen, nitrogen, and oxygen molecule, then they would each have, if it was a hydrogen molecule, it could be like 1, 0, 0, oxygen would be 0, 1, 0. And so
Right.
Yeah.
Right. Okay, so the embedding is not a dense embedding.
Yeah. Or they're represent, so they don't, or otherwise they don't have any additional features except for the type of molecule in their feature matrix. Right.
That makes sense. Yeah.
For this, yeah.
It's very, very non-continuous.
Yep. Right. The adjacency matrix is three-dimensional, adjacency tensor, as we said. So they use the graph, they use a GCN, but I think they use a variant called relational GCN, which allows also handling different edge types. This is the GCN model. We spoke about this. So this is the normalized, but this is the degree matrix. So this is the Laplacian actually. Degree matrix, normalized adjacency matrix. So H are the hidden layers, W's are the learnable weights. Okay. Aggregation is an aggregation function, so it's usually a sum, I think, or mean pooling.
So that was not very clear. So the aggregation acts on this path, on this thing for each
layer.
But also for each edge type, right? So I was the edge type. Right?
I think the aggregation must also aggregate over edge types because their definition of the representation matrix is it's a matrix and not a tensor. But you're right that like you have different adjacency matrix for each edge type, so it must collapse along that dimension with the aggregation.
But if you only have one edge type between nodes.
Yeah, but so for example, EI, the reason why it's EI and not just E is because there's multiple different, there's like maybe if there's two edge types, there's two different.
Also, you can have multiple
velocities.
edges.
So you would have, doing this operation after the ReLU, you'd have a tensor that's three-dimensional, and you have to collapse it to a matrix. Yeah.
And this thing wouldn't have to be necessarily connected, right? Because we have two edge types, say like a molecule chain, and you have one edge to the other edge type. Then if you just look at the adjacency, it would not be connected. So only when you think together.
Yeah, that's true. I didn't even think of that. So you could have like very unconnected graphs that you're describing with the different adjacency matrices.
Yeah. Just a note, they take the adjacency matrix plus identity to normalize it, regularize it, basically at self loops. We always do that. This is the degree matrix for each edge type, right? The eyes are always here. And you have L message passing layers. So hidden layers, you take the last layer as your node embeddings. And then you can also aggregate over those to generate a graph embedding. So aggregate usually means sum. Okay?
So it is a graph embedding, no?
Well, you need both. You will need both the current graph embedding, but also the node embedding. Because,
Further down, they have the equations for this.
How does the output look like? So I'm just struggling. How at the end of this network, what is the output? Like a adjacency matrix?
It's a representation matrix for each node.
You get the hedges, right? There is no softmax or anything. You get the last hidden layer.
Yeah, but which dimension does it have?
So it has n by k, where n is the number of nodes in the graph, and k is the embedding size that you've chosen as a hyperparameter.
Yeah.
And is that for so you do it for each edge type? And then
You get, I don't know.
Maybe we can draw here.
oh, sorry, for each layer you aggregate over all the edge types. But then you do the next layer.
That's what I.
So because here they are now having multiple edges of different types between nodes, right? So which means, like if you have this, you can have two edge types, right? So which means you have two different adjacency matrices, and then for each, you will have to create two adjacency matrices, and then, as Peter said, the aggregation is over all resulting matrices. So you will have to average them or sum them.
Yeah, I don't know.
Yeah,
But wouldn't it still be,
there is some sort of pooling.
wouldn't still be an adjacency matrix because D minus a half.
So these
So
diagonal.
there's like there's a Laplacian, right? There's a normalized, regularized.
Yeah, but that's still, in terms of dimensionality, I would have thought it's also.
We can look at dimensions.
Yeah.
Well,
All that matrix does is it sums up the neighboring nodes, basically, the representations for the neighboring nodes.
Because D is D was no, what was D again? D was the.
D is the diagonal matrix, which is like basically the degree plus one along of each node along each.
And E was.
adjacency matrix.
Yeah.
So just the adjacency matrix of here.
Yeah. So E is essentially adjacency matrix, right? So then
They're all square matrices.
yes, square because it's number of nodes times number of nodes.
Yes.
Type.
Yes.
Yeah.
So this is still square matrix, right?
Yeah, exactly.
Same dimensions as adjacency.
And so the whole thing is dimension of nodes times dimension of nodes, even after valuing and aggregating, right? So
You're using that to regularize.
Yes.
The D is for regularization.
the D shouldn't change the dimensionality, no?
No, to regularize
Dimensionality is the same.
the adjacency, because sometimes it can explode. I think that's why they use this.
Yeah. This is quite common. All genus do that.
Exactly. And you just use it to regularize the adjacency.
And then H would, so you would have square here, n over n. H would be n over the hidden dimension. So let's say you want,
Yeah.
so it would be the dimension, and then the weights you would have. So this wouldn't change the dimension at all. right? So you would have the H times W really.
Yeah.
So basically,
So this is
if you ignore the graph structure altogether, you just have this, right? Which becomes a normal graph, a normal neural network.
This is what D would look like for this adjacency matrix. So if you have, like, each node is connected to every other node, and you add, it's 2 plus 1 for the node itself.
Yeah.
And then by doing it, that's how you normalize it.
And because W has like a internal dimension, which is the number of possible nodes, that's why H essentially can have any sort of dimension you can have.
Well, no, it's because W is on that side, it's multiplying by the number of features. So it doesn't matter how many nodes there are. So it's like, if your matrix is N cross D, then your weight matrix would be D cross K.
And it's always
And then you get N cross K.
He was the internal node number of degrees freedom. Essentially the number of atom types.
D is the number of connected nodes.
all of them.
Plus 1.
Oh yeah.
So you're basically dividing by 1/3 in that there. So you're basically averaging over your node representations.
And K was the number of possible atoms in the.
K is the number of, it's the feature embedding space.
Yeah.
Usually, no?
Yeah, usually.
It's arbitrary. Yes. Yeah.
So N plus K is the output of the dimensionality.
All the sets, no?
Yeah.
And by K.
Well, I don't know why they'll call it Z, but we'll figure it out.
Yeah, the Z. Right. Okay. So this is we do this to learn embeddings for nodes and the currently generated graph. Okay. So let's look at the steps here. So they mentioned the two works most similar to this one. So this molecular RNN and the GCPN, I mentioned them before. Again, we have a graph. I didn't say that here. The initial embeddings are the current node embeddings because your nodes come with some sort of features. Like so you would have maybe a type of a node. I would represent the atom. So you would have the type.
That's at the start. That's the first thing.
Yeah. So for each node, you start with some features.
Yeah.
Usually you one hot encoding of the atom type.
Yeah, could be a one hot. I guess here is the one hot encoding, but you can also have any feature.
But then
Any numerical.
if this is like, but wouldn't the dimensionality be propagated through the network? If your input has to be already the dimensionality d times k, k is the number of features you have, and that by almost by definition is your one hot encoding vector.
Yes, you keep the same the dimension for the final embedding, but it's a different embedding now.
No, you don't keep the same. You can multiply it by W. The W matrix can change the number of dimensions of the embedding.
So that it becomes like
but
bundle thing.
Yeah, but do people do that?
I think they probably do it
This
here.
is what the graphs are famous.
They have.
It's arbitrary size. You can just put everything in, and you always get the same.
Because I think that they have like an embedding size of 128, but they only have like 9 molecule types. So it goes from 9 to 128.
Okay. Oh, okay. I didn't notice that, but yeah, that makes sense because your weights can control.
Yeah.
Fair. Right. So actually, let's look at the diagram here, which describes the process. Okay. So you start with no graph. You add noise here, and using this noise, you generate a new node. And actually, to generate a new node, here is the formula also. To generate a new node, you will also need this MLP, which you also train, which generates new nodes. And then between every new node and the currently existing graph, you have another MLP that generates a distribution that says, is there a edge between those or not? And then you do it with every new generated node, right? So you end up generating node and then edge, node,
So
node, edge, and so on. Yeah.
the edge NLP, this
Yes.
mu is a vector of this size of the number of
Which one? Sorry.
the edge NLP.
Yes. Here.
G mu is that?
G mu. Yes.
So
This is where I got lost.
yeah. So
I don't know.
that should be like a vector of the numbers of possible edge choices, right?
So the inputs are the current graph embedding. This is small h, and the embeddings for the jth and ith node, right? So those are the embeddings for the nodes.
What was HI again? Sorry, did the very close?
The small one. This is the currently generated graphs embedding.
RK.
So I think that HII and HIJ are
Yes.
matrix features. So they're actually just scalars, right?
These two
Of all the
scalars.
No, it's RK. No? It's like a row. It's like a row in the Z.
Yeah.
Yeah.
Right?
Yeah. I think these are the
It's a row vector. no?
yes.
Not a scalar.
These are the node embeddings for the new node. II is the new node. I think the IJ is the
H is a matrix, right?
RK vector. No.
No,
No, that's the small one.
large H.
Okay,
Large
so-
H is a matrix.
Yeah.
let's see
Yeah,
here.
it's-
HI. No, it says it's
So
a vector. Denotes the embedding of the jth node in the
Yeah.
embedding.
Yeah.
Embeddings.
Right.
HLI.
Multi-
Yeah.
No, wait, HIK.
Yeah. HIJ is a vector and HI.
This is confusing
Yeah,
because if
it
you
is.
look up, like,
Yeah.
if you scroll up, like, can you scroll up a bit?
Yeah.
It says this, oh, this is n times k.
Yeah, so that's the whole.
So what is H? Because if you go up,
Which
H
age?
is
Which
not-
age? Small or the big?
No, large. It's always large. Yeah.
this H over here, see it says n times k,
Yes.
but if you go up,
There's a
Like
chart.
the most fun I have to pay for long time.
High iteration embeddings are in vector format. Yes, right. Embeddings are in vector. Well, they are vectors, but we need to figure out the notation here because
wait, look, because over
Which
here
part?
it says HL is n times k,
Yeah.
right?
but
And
it's
then-
different there.
but
It's a small L.
No,
yeah, but
big N.
that's just the, but then it says HLI is n times k. So what's I?
Oh, those are not. So those subscripts are not indexes of the matrix.
What is it? What's I?
I think it's just a
the-
notation like the I
Oh,
element.
the
No,
iteration.
L is the layer.
Node or the next node, I think. no?
L is the number of
no,
layers
the
you went
current.
through.
Yeah, but the
the-
subscript I
Alright.
doesn't
Current
denote
iteration, yes.
row or element in the matrix. That's what I think is confusing.
Because if you
Okay.
scroll down, then they use H, I, comma, I. So they use the ith iteration, ith node.
I don't think that's what they mean. I think they don't. I don't think they mean like subscript as an index of the matrix in a matrix.
Yeah.
I think that's what's the confusion. I think
especially since you
Yeah.
grow it, right? So the dimension of some of these things won't stay constant. Because with each iteration, you would expect your matrices to
to change.
Also, how?
Yeah,
Well, because of the number.
that's why we had the
because it's-
section about notation in our paper.
You're right. The first I in the index is the iteration.
Right.
Jared said.
Yes.
But then the second I is the node.
Yeah, is the row.
Is the
Right.
row.
Yeah.
Yeah, that's why you should put a small paragraph about notation,
Oh, yeah.
saying what you mean by
No, I'm
indexes.
wondering how popular is this notation for like, I've never seen it before.
Okay, what other options did they have?
Yeah.
Where else do you put this I? Right?
Yeah.
Really,
And also I from iterations. So now it makes sense. You know?
Yeah.
So
Uh,
yeah.
right. So
Now a lot of stuff makes sense.
Oh, yes, I understand everything now.
right. So this give us the distributions to generate epsilons, And then once we have an epsilon, we have these affine transformations to generate z's, which are our embeddings.
So if I get this right, you start with noise, which creates this H. Well, actually, at the moment, you don't have any noise. It creates something. It creates something that
Noise. There's no noise here, right? You have here. You have only the MLPs. So these.
Yeah. So but then, so you have some graph embedding, which is the lowercase h in the current iteration, and then you use that to inform your next sample.
Right, which gives you the noise generating distribution
for the next node.
Yes.
And
Yes.
and the edges.
Yes.
And then you use that to then generate.
So you have distributions for nodes and edges, which you later use to generate, well, to sample epsilons.
Yeah.
So again, epsilon I and epsilon ij are the sampled noise for node and edge generation. And then you use those in your affine transformation here and here to generate the z's, which are so this gives the embedding, x here gives the node embedding, and the a, I guess, represents the adjacency matrix to decide whether there is a node, there is an edge or not.
How do you make sure that the x and the a are like so x is one part? How do you make sure it's like, you know, one atom type, not?
They do, they perform an argmax
Are they doing argmax?
on the.
Is there an argmax?
Oh, sorry, it's a bit below, yeah. So x is then b is the argmax.
Well, what are argmax? What do you mean?
AJ is the argmax.
It's over where you were showing before.
I'm still confused about what the point of the
What?
noise
What
actually is when it's in the mu actually contains, you know, the means. And
I think the
Well,
edge
'cause
is noise here because they want to avoid the discrete.
No,
discreteness of
This
the,
is called the resampling trick, which is where you want to be able to propagate gradients through Gaussian, sampling a Gaussian. So epsilon is a sample from a 0 or 1 Gaussian, and then this is just to scale it accordingly.
oh, so this you mean here?
No, I mean equations 9, and
Yeah.
they're just to sample from the Gaussian, but in a differentiable way, instead of sampling using mu and alpha. Yeah.
Right.
Right. Oh, and then this in practice, a real molecule graph is generated by taking the argmax of generated continuous vectors.
Okay.
So you take the argmax to get the types.
Yeah.
I'm thinking, so if you have a continuous dense embeddings, you just not do the argmax and end up with an embedding.
Yeah.
I guess so.
And then think how to convert it back into text. That would, yeah. Okay. Yes. Right. So we spoke about these are the inverse functions to also get epsilons from the embeddings, right? And well, now training. So to train to train this model, we want to make it also efficient. So one trick they do is that they mask some connections here, drop out some connections from inputs to ensure that this is taken from another paper, but the idea is that they mask out so that in a way that they preserve the autoregressive nature. So there is a graph, there is one node, they mask out the edges between this node and the rest of the graph, and then they train on that.
Yeah, I don't get it. This was something I really didn't get.
Yeah, me neither, but the idea is that
But it's
so
not very confident.
yes, That's the goal, right? I mean, I didn't write this paper, obviously, but do you want to train a model, as far as I understand, that can learn can learn the find function. So which takes the existing graph and the new node embedding, and then generates edges between them. So if you mask out these edges on your existing database, you train on that. The details, they don't really give much details, but that's the idea.
Okay. There's some masking that goes on.
Yes, exactly.
And it leads to making the train parallelizable.
Because you can take each node and then mask it from the rest of the graph, right? And you do it in an order. So they first order in breadth first search. Maybe we can write it up here. Right? I think that's important. So you have a graph here. So you would have this first mapping and second, right? Let's say you have these things. This would be your next one. So you kind of have layers here. So you would take, let's say, first this node, then mask this connection. This is the graph. And then take this node, mask these connections, and then there's the graph. And then you do it in order. And then we can do this in parallel because it's the same graph. That's what I got it to go from this.
Okay.
Cool. And they also have these valency constraints to make sure that the generated molecules satisfy some constraints that make sense in chemistry. And the last bit is the reinforcement learning bit, which hopefully Peter understood, because again, there isn't a lot of detail except that, well, there is the usual reinforcement learning objective with the current loss and the long-term one. I'm trying to find the so the state. Let's first define it, actually, because we need to define state and actions, right? So the state is the current subgraph, and the action, the policy network is the same as the autoregressive model, which decides how to generate nodes. So those are the policy network, okay? And the state is given by the current graph. And then you can define the loss function based on that using the usual formula.
See, like this formula, it looks confusing, but it's literally the formula for
Bellman equation.
For PPO. This is like the Bellman equation, but the way that it's modified to work for proximal policy optimization. And basically what it does is it clips rewards. And that's what you can see over there. And the whole idea is that updating a policy using you can't use data from previous what are called rollouts or like attempts at creating a molecule if every time you update your policy it's very different from the one before. So they clip rewards so that the gradient and the change to the policy is small, so you can use more data from your history in order to learn. And using this method, there's some like theoretical guarantees about having monotonic improvement. So you're always going to improve or stay the same. What?
The episodes make sense.
Yeah. So, but that's why I'm saying it looks very confusing, but it's just PPO, which is a really common reinforcement learning method for what like discrete state spaces.
And what's the reward?
The reward in this case is
it's defined for the prompt chemistry. You want some desired properties for your molecule.
Okay.
So you define the reward based on that.
But which would it be something you actually know from the molecular structure? Is it something you can potentially calculate, but it's just very expensive?
Maybe they're looking for like a chain that makes sense that provides something else.
Not make sense. I think they want not to make sense. They have this valuation thing, but I think this one is to make sure you have a molecule that's best for some properties. It's a better drug or something.
Yeah, like a drug candidate. Also, if it has like an ending that binds.
Yeah, it's good at killing threats,
Yeah,
for example. But then, of course, the question is this can very drastically change, right? If you add the next node, because
So it could be like a molecule that does nothing, and then you add one thing in it.
yeah, and also how this is the sort of thing you sort of test on that, right? So it's you probably
They use proxy rewards.
Yeah.
So like one of them is drug likeness, so likeness to other drugs which have been shown effective in what you're trying to do.
Oh yeah, we'll see in the experiments. Should we look at the experiments?
Yeah.
So because they have this different metrics, so validity means is it an actually valid molecule? So as you can see, all of them have that. All methods have that, except this graph MVP, which doesn't have any rules to enforce that, right? But because you have rules, you can actually enforce to create only valid molecules. One cool thing they found about their method is that even if you remove those rules, they actually end up generating a lot of valid molecules, which is pretty cool. Uniqueness means
how does it actually
yeah.
How does it actually work? How does the information about validity go from the reward, which is a proxy function?
The validity is not the reward. Validity, I think, is mostly enforced here.
Yeah, sure, but if you take this reinforcement array, how does the model learn what's
It's in the way. It's like what
yeah, they say it's pretty cool. They think it demonstrates that the model learns from the data, but how exactly?
So it learns.
It learns all those
from the proxy, like how similar molecules look like, from the similarity of how from the sound of how these similar molecules look like. It must somehow infer these rules of what atoms are allowed to connect.
Yeah, and what valency they will have. So it learns how to keep generating only that band, like 100%, like only in this,
Because otherwise it gets punished by the proxy. Saying this doesn't look like anything.
And you look at pure graph MVP, completely doesn't know what it's doing.
Oh, because there is no validity checks here, right? So these two don't have validity checks, so this metric is not reported for them. Yeah. So the uniqueness is what percentage of the generated molecules appear in the are different from each other.
Would that depend very much on the size of the iterations?
Uniquenesses between them.
Yeah, I mean it's a meaningful measure, because if your model only generates one molecule all the time, it's quite useless, right? So you want to make sure it generates different.
Make a unique molecule out of 10 atoms, not only 5, right? So
yes, but yes, but I'm pretty sure they have the same size for all metals, right? That's also true, but there are more metrics to control that. So novelty is that we don't copy molecules from training data, which also is important. They all are novel, which is good. And the reconstruction is, so they also did experiments of giving an existing, wait, no, this is not that. Let me check what's reconstruction.
Reconstruction is probably, you get the normalized flow sample, like the sample in the Gaussian space, and then you reconstruct the graph.
Probably. I took a note about that. Anyway, I can't find my note. But yeah, probably that's reconstructing the graph here.
The fact that novelty is 100%, is that just because the search space is so massive that it's unlikely to generate an already known molecule?
Yeah.
There's nothing to control the fact that we want to enforce the new molecules.
because it's seems very, very small, right? Because
Well, I think to me, it suggested that in a way, this benchmark has been solved and they need to find a new one.
Yes, so they study different. They do study different benchmarks. Actually, there are a few others. The zinc one
It's not a perfect.
and there is Moses, which
Yes, I
I think Moses is the more difficult version because it's bigger, it has more heavy atoms. Right, this one is harder.
heavy atoms now. What?
Heavy atoms are just bigger atoms, like as in when you go in the periodic table.
Yeah, but I'm thinking because what possibly big molecules can we make out of these? Chemically, additional technologies to do with this very big one.
Maybe that's why it's hard.
Yeah, but
Oh.
that would sort of mean that the molecule size must be relatively small. Because, I don't know, you can't.
This is a certain base. Like what's
Yeah, but if you have, I don't know, take uranium, and uranium you can only do, I don't know, uranium exploration, but anything is going to be relatively small because,
yeah.
because you don't have the valency.
Yeah.
Mahed, I just realized you were not allowed to talk. If you want to tell us about this observation, which actually is very interesting. Otherwise, I can just read out the message.
Oh, hello, Vahan. Can you hear me?
Hi, yes.
Oh, so great talk. I really like this paper as well. What I had in mind was when I read through the bit that they mentioned that they're using valency, which is more of a chemistry term. I wouldn't know much, but it's sort of constraining the optimization problem by clipping the gradients. So that might explain why it might help in convex optimization in a sense that they always get the
convex actually, because
there's a theoretical proof in another paper that says if you constrain gradients, like in GANs, I think, Wasserstein GANs, when you constrain gradients, you often have turn the convexity, make the optimization more convex, and then you that's why most of the GANs, how regardless you train them, they always get some perfect results, very different from the first generation of GANs, which always had artifacts in them, and that was why they found out that clipping the gradients, which is constrained optimization. But I was very surprised to find out the model still works perfectly even with no constraints, which is very different from usual RL models. The way that they define the initial conditions, they're very heavily dependent on that. This was very unique about this paper. I didn't understand that 100%. So I just wanted to have your opinion. Cheers.
So
I don't understand it either, but yes.
You're right that like especially actually these methods like PPO and TRPO are highly dependent, their performance is highly dependent on their initialization, but that's why they have this initial training step of actually training the model as a generative model before they use reinforcement learning. So they start with the model that's trained to do relatively well, and then they train it on the targeted task. So they have a good initial policy.
And the GNN probably helps a lot with good embeddings. But also it doesn't work perfectly. I mean, if you look at the validity with the performance, it goes from 100% to validity goes from 100% to 68 without the checks, right? So it's still far from perfect, but yeah, it works. It still works very well.
Oh yeah, I definitely agree. I was looking more on the reconstruction side of things because I would imagine getting the drug was vital for them, but I can understand they also want properties to be established as well.
Yeah.
Cheers.
What was reconstruction? I think when you give it a part of the molecule and then just.
Let me find it. I know I took a note about that, but then I can't find it. Here is the percentage of molecules that can be reconstructed from the latent vectors.
Yeah.
So construct the molecule from the embeddings.
Would this method be able to assign probabilities to existing molecules?
Yeah.
Oh, they did that actually.
They
They did an experiment about that.
I think they use validity for that. No.
No, But they did an experiment somewhere down here where they actually trained it, run it on an existing molecule, and then which would end up giving suggestions what to change about it. So they would give the existing molecule as input.
They explain their metrics somewhere.
Yeah, here, right? I just found it here. Here, if you look, 5.2. Right, and at the end, I just want to add that they also did experiments on non-molecular data at the very end, just to show that it still works. This is the experiment, which they did. Let's talk about scores generated. Oh no, this is the experiments on generated molecules, but they also did experiments on other data.
Community small and ego
I
small.
think it's this one.
It's
The-
no, it's on the page above.
The first,
It's like a citation network. Which one?
Yeah, up more.
Ah, the QED, right?
No, up more. That's true. These two.
This one. So those are. This is a community graph. This one is a citation network, I think.
Yeah.
And then they run on those different networks as an extra experiment, and then they claim that the method still works pretty well here.
And so those numbers took me a while to figure it out. There's like a correct degree, for example, in the data set, and the difference between them and this is the error between what the network generated and the data sets underlying, like maybe degree distribution or something like that. So smaller means better. I didn't really understand it that much. I just know smaller means better.
Yeah, that's all we need to know.
and what's so this graph Rnn and GraphAF, that there's 1024, is that the size of the embeddings?
They probably experimented with different embedding sizes. Yeah, yes, we can check. No,
It's fine.
nothing about that, but yeah, different embedding sizes probably. Cool. Oh, we are over time. Thanks everyone for attending. I guess we.
Thanks for having fun.
Yeah, that's the purpose, right? We want to have a fun discussion. Hopefully we'll have another in-person paper club soon. Otherwise, we'll have a Zoom version next week.
Yeah.
If anyone wants to present any fun papers, please
Yeah.
come forward. Yeah, thank you.
Very much.
So
I was actually thinking of presenting a paper on normalizing flow models, like the original paper on it, which is actually like from 2017. So it's not that old.